we left off. Today what I want to look at is one application of latitude and longitude, but it's also an application of a lot of other things. And to start with here, we're going to look at what's known as arc length. Okay? Now, arc length is a distance.
Can we ask questions from the homework?
As soon as we're done with this, I'll take questions on the homework, yes. Arc length is always denoted with a lowercase s, or it's usually denoted with a lowercase s. But it's a distance. It's a portion of the circumference, and circumference is the distance all the way around a circle. So it's a portion of the circumference, and it's determined by a central angle. Okay? Now, I'll show you this here so you know what we're talking about. A central angle, remember, is an angle formed by two radii, which means its vertex is going to be the center of the circle. Okay, you can't use this formula, you can't find arc length this way unless the vertex is the center of the circle. Okay?
That's the formula?
Now, this is the formula, yes. If we know a central angle and the radius, whether the angle is in radians or whether it's in degrees, we can use that to find arc length. Okay? Now, I don't want you to just memorize this formula, although you do need to memorize the formula. I want you to understand it, because if you understand it, it's really not a hard formula to remember. What this is saying is that if we make a ratio, if we find what ratio our central angle is of the complete circle, whether 2 pi or 360, if we find that ratio, then our arc length is going to have the same ratio to 2 pi r. And what's 2 pi r? The circumference. Okay? The circumference. Alright, so whatever fraction of the full rotation our central angle is, our arc length will be that same fraction of the entire circumference. Okay? Now, as an example here, I give you a circle where the radius is 5.5 centimeters and our central angle is 70 degrees. So if I were trying to find our arc length s, I would see that s needs to go over the circumference. So 2 times pi times our radius, 5.5. And that's going to be equal to our central angle, 70, over what?
360.
Over 360. Okay? Over 360. Make sure if your angle's in degrees that you do it in degrees. You put it over 360. Okay? If our angle was in radians, we'd put it over 2 pi. So now, you guys know how to solve a proportion. This is 11 pi, so I would just multiply both sides of the equation by 11 pi, so I'd have 70 over 360 times 11 pi, right, and we would simplify, okay?
Don't you do the cross multiplication? Not in this.
You can. In this case, because the s is all by itself in the numerator, if we just see it rather than as cross multiplying, see it as just undoing the division.
Okay.
So, I mean, you'll get there eventually. It just saves a step.
Okay.
So, let's see. S would then equal how many centimeters? 6.72 centimeters. Okay? So that's how far around the circle S takes us. Okay? Yes.
11 pi.
11 pi. Yes, this is 11 pi. Because it was 2 times 5.5.
I see some SATs all the time that I never know how to do it.
Oh yeah?
Never thought it was.
Well, now you know. Yes.
If I saw a problem on the homework with this, if S was like
like not this space right there, but like the rest of the circle, how would you find that?
Okay, that's a good question. If S were over here.
Yeah.
Okay, you could do this one of two ways. You could either do what we did, but it wouldn't give you S, it would give you this, and then subtract that from the whole circumference.
How do you know what the circumference is?
Well, you just have to do 2 pi r.
Okay.
Okay, so you could do it that way. Or, what I would probably do is, if that's 70, that means this whole angle would be 290 degrees.
And then you just do the same thing.
And you do the same thing but with 290 instead of 70. And that would be a little bit faster in the end. So, good question. Alright. Now, we can also figure things out like, what would the angle have to be in order for it to cover a certain arc? Okay, for example, here we have a central angle. Here, I'll make it a little more angular here. Okay, here we have a central angle theta, and I want the arc to be 38 inches. Alright, so let me draw this all the way to here. Okay? What arc, or what angle will give us an arc that's 38 inches long? And guys, this is the kind of thing, obviously we could talk about it directly in terms of distance, but let's say you were designing something, and whatever you were designing needed to lift something, you know, up off the ground a specific height. Alright, well, you might, at the top of that, use a wheel. Alright, maybe whatever we're trying to lift is attached to a cable. Okay? And we want to lift it specifically, let's say, 4 feet off the ground. Well, we would have to figure out how much to rotate this circle, or this wheel, in order to lift 4 feet off the ground. Okay? So let's say the radius here was, 1 foot. Okay? If you figured out 2 pi r, 2 times 1 is 2 times pi, so our total circumference is 6.28, 2 pi. Well, 4 feet is almost 6.28, so it would have to rotate about that far around in order to lift it exactly 4 feet off the ground. So if you were programming the machine that was going to be doing this, you would need to tell it how far to rotate. How many degrees would it need to rotate? Or if you weren't doing degrees, if you were doing it spin for this amount of time, you would figure out the amount of time by finding that angle in there. Okay? So it's kind of an interesting concept. We're really translating what in this case would be a linear measurement, 4 feet straight up, into an arc length. Okay? So that's just one of a lot of different applications of this, where we would want the actual angle. Okay? But finding the angle really isn't too hard. Okay?
Is that a 0? The one below 12?
Yeah,
That's a theta. That's the letter theta. It's for an angle.
Oh.
Okay? You'll see a lot of Greek letters in trig. And the nice thing is you don't even have to know what it's called. If you just recognize, hey, whatever that is an angle. Okay? You'll probably see theta and alpha and beta, maybe a gamma. Alright, you might see a phi or xi, maybe even an omega. Okay?
Omega.
So you might.
Omega.
that's a lower. They're all lowercase letters. Capital Omega is like this.
Yeah.
So that's one you've probably
I think that's
seen
rough
before.
physics.
But anyways, yeah. If you see any weird symbols, they're probably just Greek letters naming angles. Okay, so if you want to look them up, you can. But let's take a look at how we would find theta in this case using our proportion.
38.
We asked for it in radians, right? So we would put theta over,
360.
2 pi.
2 pi.
Right.
if it was in degrees, 2 pi for radians. Okay.
Oh, radians.
And then that's going to equal our arc length over the circumference. Well, we know the arc length is 38 inches. Good. What's our circumference here?
24 pi.
Pi 12.
Good. 2 times pi times 12, which is 24 pi. And here's something, as you go to solve these, I would recommend don't actually multiply by the pi's unless you have to. Okay? For example, in this case, if I'm solving for theta, I would multiply by 2 pi,
And you cross out the pi.
and the pi's will cancel out. So you don't even have to multiply. Or you don't even have to use the 3.14 and so on. Okay? So here, theta is going to equal 76 over 24, which reduces down to 3 3/24, which is 3 1/6 centimeters. Okay, or not
1/8.
centimeters, inches. Sorry,
1/8.
That's what I
3 1/8. Wait a sec, did I do that? Oh, it's 4. Sorry, it's 3 4
Oh my.
24ths. I knew it was supposed to end up as sixths. So 3 4 24ths is 3 1/6 inches. Okay?
So what did we get?
So we found, wait, not inches. That's I'm messing this up bad. This is radians, this is an angle. Sorry. That's radians.
Oh, find the central angle.
Yeah, we're finding the central angle in radians. I'm stuck on, lifting boxes off the ground.
I was doing it in degrees, and I was like, what?
Yes.
What is that? But then it's the measure of the angle?
That's the measure of an angle. Now let's think about that. We know that pi is 180 degrees, right? So 3 1/6 is 3.1666666. So this is what? If we were thinking in degrees,
Nearly a pi.
it's a little bigger than pi, right?
Yeah.
So our angle would be a little bigger than 180 degrees, okay? So in reality, it would look something like this, almost like a straight line, but it's just past 180 degrees. We'd have to rotate. Yes?
If we had to find it in degrees, would we do theta over 360 equals C? Okay.
Yes. Any other questions?
Oh, yeah. If we're doing degrees, would we keep the pi in the answer, or would we put it in, plug it in?
The only time I want you to leave pi in your answer is if either they ask for an exact answer, they're telling you leave pi in your answer, or if you're giving an angle in radians and they don't cancel out, just leave it in terms of pi.
Okay.
Okay. In this case, the pi's canceled out, so even though we're in radians, you don't see the pi there. If we wanted, we could divide this by pi and have that times pi, but we don't need to do that. Yes?
Will you tell us if we need to leave it in pi on the test, or
Mhm.
will you expect us, like, no?
Well, I mean, if I ask for an angle in radians, just what I said here, I would expect. You know, if the pi's cancel out, just leave it what it is. If the pi's don't cancel out, then leave it in terms of pi. And as we'll see, we're going to be doing stuff with the unit circle. Those things I will expect you to leave in terms of pi. But we're going to get to that. Yes?
How did you guys sorry in
That was given to us.
Oh.
We wanted to figure out the angle that would give us an arc length of 38 inches. Alright, so that's an application here with radians and degrees. It's one thing we can do with circles. Are any of you in HL physics? You are? Okay. So, one thing you'll run into, if you haven't already, linear and angular speed.
We just started that.
You guys just started that, okay. We're not going to spend time in this class doing it, but I just thought it was interesting. Your book talks about it, so I thought I'd show it to you. If you're curious about it, you can look it up. But basically, if you incorporate arc length along with time, you can figure out how fast something is moving around a circle, okay? You know, it's hard to tell how fast things are moving around a circle because they're not going in a straight line. It's hard to tell how far they actually went. But if you use arc length to find that distance of how far they went, then you can divide by time and get the speed, all right? The angular speed, got to have your angle in radians for this, but you divide your central angle by time, and that'll show you how fast the angle is growing. Okay, how fast is that angle getting bigger, not necessarily the arc length getting bigger. Okay, so just an interesting thing I thought I'd point out for those of you who are curious and like to look into some stuff on your own. All right, at this point, some folks asked about questions on the homework. Since we finished the entire section, I know there were a couple of things that involved arc length. I told you you could skip those, but you may have tried it and now you know. But are there any questions from the homework, or what questions did we have from the homework? Yes, Jen?
I think it was on the one with the coterminal, the coterminal angles.
With the
I just-
radians?
Yeah, why did they add 2 pi and subtract 2 pi? And then on one of them I know they added 4 pi and I didn't know why.
Okay. For the coterminal angles, if you remember, here's 11b. Coterminal means they're in standard position, and the terminal side, this ending side, is the same. Okay? So what we said, and we did all of them in class, we did with degrees. Okay? But we said that to find coterminal angles, you could either rotate backwards from 0 to get there. And what that ended up giving you was the original angle, but minus 360 degrees. There we go. So that's why they did the angle minus 2 pi, because that's a full rotation.
2 pi is a full, because pi is 180 degrees.
Yes.
Oh.
Okay. To get a coterminal angle in the positive direction, you would have to rotate around once completely, then rotate to the terminal side. So that ends up adding an extra 2 pi to it.
So why on number, I think it was 14.
So if you add, then you're going the other way. Or no?
If you add, you'd be going.
If you add, you're going counterclockwise.
And then you subtract, you're going clockwise.
Yes.
Okay, that's what. What I did is that, like, for number 11, for pi over 6, I did like 180 over 6, and then I got 30 degrees. and then I just like subtracted 360 minus 30, and I got like negative 330. Is that right?
You got negative 330 and then what, like a
Okay.
positive 390?
No. I got 30 degrees for that little part.
Oh,
And
you were
then-
saying the 30 was your coterminal angle?
I don't know. I
Okay.
just like figured out the angle inside and then like the one outside. And
Okay.
that's what I used.
Alright, you're on the right track with that. If you're given stuff in radians, in general we don't change to degrees unless we're told to. So, and they said find the two coterminal angles in a radian measure. Now, what you could have done is said, oh, well now I know it's negative 330, so then convert that back to radians by multiplying by pi over 180. That would have worked, and that would have given you 11 pi over, or negative 11 pi over 6.
Well, what did they mean by coterminal again? Just that like together they equal 360, right?
Well, no, coterminal means they share that side,
Oh, okay.
okay? They're in standard position, but they might rotate backwards and have that side, or they might rotate all the way around and then get to that side,
Oh, okay.
or they might rotate 10 times around and then get to that side.
So like if I changed the two that I got into radians, I would have gotten it.
Yeah, I think if I'm understanding you right, I would think that's the case.
Oh, okay.
Why on number 13 would you have to add 4 pi to one of them?
Okay, let's see. It would be A, I think. Yeah, A. Basically because, alright, negative 9 pi over 4, if I were to draw this, that's negative 2 1/4 pi.
So that's like
Alright.
negative 2 and 1/4.
So, negative 2 pi would go around once, and then another 1/4 pi would put us right here. Okay? That's a negative 9 pi over 4. Okay? Now, the directions said to find one positive and one negative coterminal angle. Alright? So, if I were trying to find the positive coterminal angle, so I added
Right.
2 pi, then that would have actually given me this. Okay?
Can you, how do you,
Negative 9 pi over 4 plus 2 pi is still going to be a negative pi over 4.
oh yeah, okay, I got
Okay? So that actually gave me my negative coterminal angle.
it.
So now if I add another 2 pi, I'll finally be in the positives. We had to add 4 pi because we were more than one rotation into the negatives. So we had to get all the way up into the positive angles. Alright, so negative 9 pi over 4 plus 4 pi, we're just adding another 2 pi to this. And then that will actually give us that angle right there, which is a positive 7 pi over 4.
It's not, like, I guess just because there's not like one set. Like,
Yeah, most of them are gonna work this way, because most of the time we're given an angle between 0 and 2 pi to begin with, so you can always just add 2 pi and subtract 2 pi. The only time that's not the case is if the angle you're given is either smaller than 2 pi, or negative 2 pi, or it's bigger than positive 2 pi, so you have to do more than one rotation back to get the other side. Alright, any other questions from the homework? Did the conversions? this part here you might have skipped because we hadn't gotten there yet, but now you should be able to do that. One part I will point out, because this is a good transition. How many of you got to 75 and 76? How many of you did those two? Okay. If you had, you would have noticed a number of these actually were the same. Okay. Now the fact of the matter is, by the end of the week, we'll have seen all of these, and you'll be relating those to each other quite a bit. Okay. Eventually, we'll have all of these memorized, and you'll know your whole unit circle, which is really, really helpful. Okay. It may sound like a ton, but there is a pattern to it, and it's not too bad once you get the hang of it. All right.
Is that the whole unit circle?
No, not completely. So
I'm pretty sure they did the song for last year or something.
they had a song for it. I think there is a song, but I heard someone sing it once, and it kind of just became mumbling quickly after a few lines, so I didn't catch a lot of it. But I'm sure there's something out there. People make songs to help them memorize. There's actually a good pattern to it too. So, well, let's talk about what the unit circle is first of all. Okay, I've mentioned it a number of times. So we're going to spend a few days here looking at sections 2 and 3 kind of together. I thought they went well together rather than having them as distinct sections. So what is the unit circle, first of all? Well, it's centered at the origin, and it has a radius of 1. Okay. Radius is 1, it's centered at the origin. If you remember your conics from Algebra 2, the equation of the unit circle would be x squared plus y squared equals 1. But that's our unit circle. Now you'll see every point on the unit circle obviously has an x and y coordinate. But we could make a triangle, a right triangle, with the x coordinate and the y coordinate. But with all of these, because the radius is 1, the hypotenuse of that right triangle will always be 1. So we're going to use that here in just a moment to help us find a number of points on the unit circle. Now, let me bring this up here. I want to show you the final product that you're going to have once we learn all of it. There we go. Oh wait, it's under here. And my mouse. All right. I want you to see the final product, because this, by the time we're done here, all of you are going to have this memorized. But I want you to show you where we're headed, and then you might see why we're going to kind of build it slowly, kind of one step at a time, and we'll see some patterns in here that'll help us remember it, okay? Whenever this decides to pop up. Evidently wanting to work really, really slowly today. Ah, here we go. Okay, so the final product is, yes,
Oh boy.
that was my plan, to make it suspenseful. Here we go,
It looks very low.
if it'll actually show.
So helpful.
I don't know why it decided to work so slow. Here we go.
Oh.
Alright, so by the time we're done,
Come on, I have my
Oh.
you guys will have all this memorized.
We did this.
Alright?
I already got this down.
I know it's right.
Yeah. Those who have the photographic memory, you have it down already.
Oh,
So,
got it.
It's like first grade.
I know.
but here's the thing.
Which one?
Listen up.
Yeah.
You'll notice a lot of the same numbers in here. Okay? You'll notice a lot of the same numbers or a lot of similar numbers at least in here.
Because
Okay.
they're all
Now I don't want to
same
give too much
degree.
away, so I'll put that away for the moment.
Suspense.
And I want to show how this is constructed. Alright? Because it's helpful to understand. First of all, we're going to focus on the angles. Alright? Here's two smaller versions of the unit circle, and we're going to focus on just this first quadrant today. Right? But you'll notice we're cutting our unit circle in two different ways. One, we're cutting each quadrant in half, alright, which means, you know, if we're talking about angles, then, you know, this is going to be 0 degrees, and this up here would be 90 degrees, alright? So if we cut the triangle like this, where we're cutting each quadrant in half, what angle is that going to give us here?
45.
45, okay? And that's this middle one right here, 45 degrees. Okay? So that's 45 degrees. We also cut the unit circle to where each quadrant is cut in thirds. Alright, so you'll see we have two different angles in there. That's what these ones are. And if we're cutting the quadrant into thirds, then what are these two angles?
30 and 60.
Yeah, there we go. 30 degrees and 60 degrees. Okay?
Yeah, you know that?
Because we're cutting the quadrant into thirds. So 90 divided by 3 would be 30, and then 2/3 would be 60.
Oh, okay.
Okay? Alright. Does everyone follow that?
Sure.
Alright, good. Good. Now, let's look at it in radians. Let's think in terms of radians. 0 degrees is how many radians?
Zero?
0. Not a trick question.
Oh.
Alright, so 0 radians. Now, you guys know that pi is how many degrees? 180. So 90 degrees would be
Oh, a half.
pi over 2, a half of pi. Pi over 2. Okay? And now if you just think in terms of, alright, what would I have to divide 180 by to get this angle? So, what would we have to divide 180 by to get 60?
Pi over.
We'd have to divide by 3, so it is pi over 3. Okay? 180 divided by 3 is 60, so pi over 3 is the same thing in radians.
Just count. Oh, no, then go pi over 4, then pi over 5 or something.
Well, this one is pi over 4,
Pi over 6, so.
okay? Because 180 divided by 4 is 45, so that's pi over 4. And then I heard some people say it here.
Pi over 6.
Pi over.
Pi over 6, good. Pi over 6. 180 divided by 6 would give us 30, so this is pi over 6. So that's the radians and degrees in the first quadrant. So you already know all except for the points here in this first quadrant. Alright?
Yeah.
And the nice thing is, once you learn the pattern, getting the angles in the other 3 quadrants is actually really easy. Alright, so we'll learn the pattern later on this week.
But Mr. Erickson,
Yes.
are we going, is it going to like make like 30, 60, 90 triangles with the other one? Like, you know, how you had like the 45, 45, 90 ones?
Yeah, like those?
Yeah.
Yeah. Okay, and that's actually what we're going to look at next is what are the values, and I'm talking about the coordinates of these points. What are the values of the x and y coordinates at each of these points? And by the way, it's 144. Those you have to go. Okay. For that, we're going to use the 30, 60, 90 and the 45, 45, 90 right triangles. Okay? Now, let me bring this down.
Sorry.
So, for example, if I'm looking at this triangle right here, okay, it's going to have some coordinates x and y. This is a 30-degree angle. We already knew. This is a 60-degree angle. Okay?
Why you?
And then we have our pattern. Remember, this is a unit circle. If it's a unit circle, the hypotenuse has to be 1, right? Because the hypotenuse is a radius. So that's what I've drawn for you up here. Alright? Now I want you to take some time on both of these, both for the 30, 60, 90 and the 45, 45, 90. Try to find these other two sides. Okay? It'll be a little bit of a geometry review for you.
Oh,
Okay?
okay, I got it. I was gonna ask them, what is the y x root 2 is equal to 1? Okay,
Yes.
I got it.
Okay. You can ask a neighbor for help if you're a little stuck.
Don't you just plug in X?
Yeah, figure out x and then plug it into the pattern on the other two sides. And just leave them in a radical form, okay? Don't do decimals. All right, head out to the